Okay, we're talking about standing waves. Standing waves are waves that are regularly repeating on themselves, and the fact that they're going to appear like they're standing still. A common thing would be a jump rope. If you had two people playing with a jump rope like this, you could get a standing wave that looks like this. This is probably the most familiar one that most of you have seen. You know, the jump rope thing. I don't know. It's not a very good person. But in the fact that they're wiggling back and forth, realize it's moving so fast it appears to be standing still. Well, if I look at it, this is the part of the wave that I'm looking at. If I was to take a snapshot, I'd only see one part of it. That is half a wavelength, lambda over 2. Now, if they shake it with a greater frequency, so my people are still here, if they shake it with a greater frequency, they could get this. And that would represent a full wavelength there. If they shake it even faster, they could get this. Like that. If they shake it even faster, I'm going to screw this picture up eventually. Did I do it right? I didn't. I have 5 bubbles and there should be 4 bubbles. I like to call that a bubble, but you don't have, you can call it anything you want. This would be 3/2 lambda, 1.5 wavelengths. One wavelength would be from there to there, and then you have an extra half a wavelength. This one would be, well, 1 wavelength there, 1 wavelength there. So this would be 2.5 lambda. Another way to potentially see that is to go through and simply do this. Okay, that's 1 wavelength. There's a second wavelength, and then there's a half one. Remember, if you take a snapshot of it, it's going to be where that blue line is, not where the red line is. Now, there's some important things about this. This point right here is called an antinode. It's where, excuse me, that point right there is called a node. A node is where there's no movement. There has to be a node here. There has to be a node here. Right in the middle where I have maximum movement, I get an antinode. So right here, node, antinode, node, antinode, node, antinode. Like that. And realize that antinodes are always separated by half a wavelength. It really doesn't matter which wave you're talking about. The antinodes are still separated by lambda over 2. Now, this is sometimes called a resonant spacing, because resonance is where I'm going to get maximum vibration. Resonance spacing is always going to be lambda over 2, regardless of what the wave is. So, if one thing you could do is, let's say, for example, that, let's do an example. I have this. And I tell you that this is 6 meters. If that's 6 meters, what's lambda going to be? Well, figure out how much each wave takes. Lambda would be this. And again, I think it helps to maybe even do it in a different color or potentially squiggle the lines or something like that. That would be a wavelength. Well, if this entire thing here is 6 meters, lambda has to equal 4 meters. If you know the wavelength, you can also then start applying equations. Well, the most common equation we're going to use with this is this one. V is equal to F times lambda. Now, I can get lambda from looking at that. Frequency will generally have to be given to me, and then I can calculate speed. But as long as you know 2, you know the third one. So let's play with that a little bit later. Again, well, just a quick review. This depends only upon the medium. In other words, what it's in. So what happens after that, if you stay in the same material, as F goes up, lambda goes down, and of course vice versa, as F goes down, lambda goes up, as long as you're in the same material. Now the other thing is kind of important to understand. It depends upon the medium. So it depends. You can change the medium. One way to see this is a guitar string. With a string, what happens is, as I increase tension, increasing tension in the string is almost like I'm creating a new medium. So therefore it changes how fast it moves as you pull it tighter. And more on that, that'll probably get its own video when we talk about that to a greater detail. So velocity equals frequency times wavelength. Now there's two different types of pipes that we're going to encounter. There's open and closed pipes. An open pipe is, wait for it, open at both ends. A closed pipe is closed at both ends. Now, if I look at this and I have something that looks like that, I'm going to get a standing wave that looks like that. This is going to be an antinode, and this is going to be an antinode. I would also get it again at this. Let's see if I can draw this good like that. I messed up my drawing. Let's do this. Oh, I do it 2 foot long. That's why I run into a problem. I'm going to get this. And that. Okay, I'm going to get an antinode and an antinode. This is lambda over 2. To figure out what this one is, do this. You go trough, crest, trough. That whole thing is lambda. And you can see there'd be a pattern there. You'd get, for an open-ended pipe, because you're going to have an antinode at both ends, you'd have lambda over 2, lambda, 3 lambda over 2, 2 lambda, like that. There's a pattern that starts out. Now, with a closed-end pipe, it's a little bit different in the fact that at the bottom of a closed-end pipe, I'm going to have a node, because I'm going to close that end, so I'm going to limit my vibration. Well, it turns out that's 1/4 of the wavelength, and the lab should reinforce that. You're also going to get another one as you go up when you get this. So node there, antinode, back through a node, back there. Now, the key thing here is we have node, antinode, node, antinode. This turns out to be 3/4 of a wavelength. So again, I'm gonna get this pattern here. I'm gonna get 1/4 lambda, 3/4 lambda, 5/4 lambda, 7/4 lambda, etc., etc., etc. Now I'm gonna get maximum when I get maximum vibrations at the top. This is one of the ways musical instruments work. The next thing we have that we probably, while we're talking about it now in musical instruments, is the fundamental. The fundamental is the basic frequency that you're going to be able to get, the basic note you're going to be able to get. And then I have overtones. An overtone is twice the fundamental, like that. And then 3 times the fundamental, and 4 times the fundamental, and 5 times the fundamental. I'm going to get again different sounds, and that's kind of how musical instruments work. They work by putting these different overtones together to create the sound. So if your basic frequency is 200 hertz, and that's the fundamental frequency of that, so that's your fundamental, then you're going to have an overtone at 400 hertz. You're going to have an overtone at 600 hertz. Like that. Now, important thing to remember with this, velocity equals frequency times wavelength. So let's do this. V is equal to F lambda, most important wave equation, and T period is equal to 1 over F, so therefore F is equal to 1 over T, so V is also equal to lambda divided by T. Well, that's nothing more than distance divided by time. Those speeds are the same. Okay, more coming up in your next one.